Good morning. Welcome to the class on manufacturing process 2. Today we are going to discuss on electrochemical machining. I am Dr. Soumitra Pal. This belongs to the module number 9 on non-traditional manufacturing processes. This is lecture number 9.5. Before starting the actual lecture, let us go into the instructional objectives. Instructional objectives, as you know by now, are the points or topics that you are going to learn once you go through this lecture. In today's instructional objective, once you go through the lecture, you will be able to identify the electrochemical machining, which is in short known as ECM, as a particular type of non-traditional processes. Already we have covered a few non-traditional processes. You know, abrasive jet machining belongs to mechanical group of non-traditional processes. Similarly, ECM you would be able to associate with a particular type of non-traditional process. Once you have done that, you would also be able to describe the basic working principle of electrochemical machining. You would be able to draw the basics of ECM so that you can describe the working principle along with figures. In electrochemical machining, electrodes are used for machining. So, across the electrode there will be potential drop. So, you would also be able to understand and schematically draw the tool potential drop. In any non-traditional machining process, material removal rate is one of the major machining characteristics. It is to be enhanced without sacrificing the product quality. So, in today's lecture you would also be able to describe material removal mechanism in ECM. Later on you will be able to identify the process parameters and most importantly develop material removal models in electrochemical machining. Now, electrochemical machining is a dynamic machining process. So, analyzing the dynamics of electrochemical machining process is also very important. There are different modules in electrochemical equipment, so they are to be identified. Like any other machining process, there are specific application areas for ECM which should be listed, and we would also give you schematics of those application areas. So, this briefly describes the instructional objective. Now, let us go into the classification of non-traditional machining processes. This is your 5th lecture on non-traditional machining process module. So, already you have gone through quite a few of them, and in the process you have learned that there are mechanical processes, there are electrochemical processes, and there are electrothermal processes and chemical processes. Before today's lecture, we have already covered electrodischarge machining in the previous lecture. We have covered abrasive jet machining, ultrasonic machining, water and abrasive jet machining, which were belonging to mechanical process. And today our aim is to understand the basics of electrochemical machining, which belong to electrochemical process segment. Within that process segment there are two more processes. One is electrochemical grinding, another one is electrojet drilling. However, today we will concentrate on ECM or electrochemical machining processes. Now, let us come into the electrochemical machining process. In electrochemical machining process, like any other process, we require a workpiece as well as we require a tool. So, this is my tool and this is my workpiece. They are emerged in a solution just like electro discharge machining, but this solution is not dielectric like electro discharge machining. This solution is that of a electrolyte. Typically sodium chloride salt is used to prepare a aqueous solution and the electrolyte. What is electrochemical machining? Briefly, it is just the opposite of electrochemical deposition. This is a controlled anodic arc, canodic dissolution. So, this is my workpiece. So, this was my workpiece and this is a anodic dissolution. So, this is controlled anodic dissolution. So, if you look here, the workpiece is connected to the positive terminal and your tool is connected to the negative terminal. What is the next point? We have already covered. Tool is my cathode and workpiece is my anode. There are other characteristics of ECM process as well. Typically, the voltage which is applied is a low voltage, it is low potential, but the amount of current which passes through this particular electrochemical cell is rather high. Now, there is a machining gap. Initially, the machining gap could be rather high, but during steady state operation, the tool has to be fed continuously so that a specific gap can be maintained. And as we have already said, the whole thing has to be immersed in a electrolyte solution, and sodium chloride or sodium nitrate, these aqueous solutions are the typical electrolyte solution which are used in electrochemical machining process. Now, let us schematically see what happens typically when someone is trying to machine a ferrous material. Different types of materials can be machined, but for today's example schematically we want to show what happens when it is a ferrous material. So, let us come to the graphics. So, this is describing the electrochemical process and this is my workpiece and this is my tool. Okay. And once we apply a potential difference, then what happens? Because of electrochemical dissolution, this is my electrolyte, this is my electrolyte, and the electrolyte could be sodium chloride electrolyte. So, what happens? As because it is aqueous solution, in this particular electrolyte you would have chlorine atoms. So, these are your chlorine ions. Similarly, you would have sodium ions. You would also have hydroxyl ions because water will dissociate, and once the cell is switched on, once current is passing through it, as because the workpiece is made of ferrous ions will react with chlorine ions as being indicated here to form ferrous chloride, and they can also react with hydroxyl ion to form ferrous hydroxide. What happens to the hydrogen ions? These are the hydrogen ions. Hydrogen ions would be positive. So, they will go towards the tool material which is connected to the negative terminal and hydrogen gas will evolve. So, in summary, what happens in electrochemical machining process? I have a workpiece, I have a tool, I apply a particular potential difference. The tool is connected to the negative terminal and the workpiece is connected to the positive terminal, and the whole as well as workpiece and the tool, they are immersed in a electrolytic solution. Typically sodium chloride or sodium nitrite solutions are used as the electrolytic solution. I apply a DC current and the typical voltage applied is 2 to 35. As because it is sodium chloride solution, in the aqueous solution I would have sodium ions, I would also have chloride ions, and once the cell is switched on, iron will come out of the workpiece and react to form sodium chloride or sodium hydroxide, and hydrogen will evolve from the cathode. In this way, due to controlled anodic dissolution, we will get machining on the anode or workpiece. Now, you have already seen this is my workpiece which is anode and this is my tool which is cathode, and I am applying a potential difference between them. Let us try to study how that potential difference drops in a particular ECM cell. What we have here, this side is my anode and this side is my cathode. So, the total potential drop over here is called the anodic potential drop, and the total potential drop here is called the cathodic potential drop. What is this separation? This is the separation or distance this is the distance between my two electrodes. This is cathode, so this has to be my tool, this is anode, so this has to be my workpiece, and this is the distance of separation. Okay. Now, first drop is the anodic potential drop at the anode, and similarly the cathodic potential or cathode potential drop at the surface of the cathode, which is followed by the activation over potential. You require a bit of over potential to establish the flow of electrons and ions through the cell. So, this is the activation over potential. Then you have ohmic potential drop within the cathode and anode, and similarly you have the concentration potential drop, because once electrochemical machining or deposition starts, there would be some concentration gradient near the electrodes, and then from this point to this point you have the electrolytic drop through over the almost complete separation distance between my cathode and anode, or in other words tool and workpiece. So, in this way the potential drop occurs in electrochemical machining. To have electrochemical machining, I have to provide a potential so that all these potential drops can be achieved and gone beyond, so that there is a electrolytic drop which drives the cell or machining process. Now, let us come to the process parameters. As you know, if you cannot identify the process parameters, understanding the basic process becomes difficult. Without knowing about the process parameter, you cannot optimize, you do not know what is the effect of a particular process parameter on one of the most important machining characteristics, that is material removal rate or product quality. So, we need to understand what are the process parameters first for any machining process, and today we are going to do that for electrochemical machining. As we said, one of the major area or major item in electrochemical machining is the power supply. That means what kind of power we are going to give. Generally DC power would be given. We have already identified it is a low potential, the voltage applied is rather low, around 2 to 35 volt. However, the current capacity of your power supply has to be very, very high, around 50 to 40,000 ampere. More so, the process is identified not by the current, but by the current density. Current requirement is very much important for the machine manufacturers, but current density, this particular term is very, very important as far identifying the process is concerned, and the current density, as you can see, is around 0.1 ampere per millimeter square to 5 ampere per millimeter square. So, current density is nothing but the current divided by the area of the electrodes. Now, we have already understood that there has to be a working gap between the electrode and the workpiece, and that working gap is around 0.1 millimeter to 2 millimeter. Just like electrode discharge machining, as we have discussed, in ECM as well there is some amount of overcut. When we go into the schematic of the actual drawing, we will once again show you how to control that overcut. As we said, to maintain a particular working gap, the tool has to be fed, and it has to be fed with a particular feed rate which varies in terms of 0.5 to 15 millimeter per minute. You can see the feed rate is rather high, 15 millimeter per minute. So, the material removal rate in electrochemical machining would also be high. Electrode material can be copper, brass and bronze. It can machine any material which is electrically conductive irrespective of their mechanical properties, and the tool material are typically the copper, brass or bronze. Surface roughness obtained are very good. It is as less as 0.2 to 1.5 micron, but quite often it is rather less. Once again, we have the electrolyte. So, electrolyte also plays a significant role in electrochemical machining. Typically, either aqueous solution of sodium chloride or sodium nitrite is used. A temperature is required to be maintained, and a flow rate has to be maintained, because during the machining process, sodium, if you are machining iron based alloys, iron chloride or iron hydroxide are forming during the machining process. Those are sludges. If they are not removed continuously, your molar concentration of the electrolyte is going to change. Thus, you need to have a substantial flow rate so that those sludges can be removed continuously, and for that you also require a pressure. Typically, the dilution is around 100 grams to 500 grams per liter of water. So, 100 grams of sodium chloride is formed with 1 kg of water or 1 liter of water to get a particular electrolyte in for electrochemical machining. Now, let us come to the characteristics of electrochemical machining. In characteristics of electrochemical machining, we will be talking about what are the typical properties required of tool material and work material. Tool and work material, both of them are to be electrically conductive. So, it is very similar to your electro discharge machining. Just as in electro discharge machining, your tool and work materials are to be electrically conductive. Similarly, in electrochemical machining, they are to be conductive. If you remember, as far as abrasive jet machining, water jet machining, abrasive water jet machining and ultrasonic machining was concerned, there the domain of the energy was mechanical in nature, and thus you do not require the material, the work material to be electrically conductive. But here, as well as in electro discharge machining, they are to be electrically conductive. What is the next characteristics? The material removal characteristics. Material removal occurs by atomic level dissolution. As we said, electrochemical machining is just the opposite of deposition, electrochemical coating or deposition process. So, it occurs due to atomic level dissolution, and as because it is atomic level dissolution, the next point is very simple to understand. You get a very excellent surface finish. Thus, as because it is atomic level, surface finish expected would be very good, and here you can get a surface finish as low as 0.1 to 0.2 micron RA value, which is very good. Now, let us come to the another point. In any kind of mechanical grinding or machining process, or even in electro discharge machining process where there is lot of thermal effect, you would be getting lot of temperature damage. So, there could be residual stress, but in electrochemical machining almost stress free machine surface are obtained. There is absolutely no residual stress. So, in strategic sectors where the machine component should not have any residual stress, this is a very good solution, electrochemical machining. And as well as there is no thermal damage, rather as because there is no thermal damage and as because the dissolution is atomic level, we get residual stress free machine surface. Now, let us come to the modeling of material removal rate. Till now we have discussed around 4 different non-traditional machining processes, and in all those non-traditional machining processes we have tried to model material removal rate, because material removal rate determines how fast you can machine. So, how much would be your machining time, so that in turn will determine what is your productivity, even what would be your profit rate and all those functions. So, it is a very important phenomena to understand, so that later on it is because it is later on related to even techno-economical viability of that particular process. So, now let us come to the modeling of material removal rate in electrochemical machining. We have already understood material removal occurs due to atomic dissolution, and as we know, electrochemical dissolution is governed by Faraday's laws of dissolution. So, this is a very simple law and which can be used to model electrochemical machining process. What the law says? It says amount of electrochemical dissolution or deposition. This law is not only for dissolution, it is equally applicable for coating process or deposition process. So, amount of electrochemical dissolution or deposition is proportional to what? Amount of charge that we pass through the electrochemical cell. This is the first statement of the law. What is the second statement of the law? Once again, amount of material deposited or dissolved, in case of machining it would be dissolved, the amount depends on or proportional to something which is called electrochemical equivalence, which is typically denoted in the industry by ECE. And what is this ECE? ECE is related to the ratio of, it is the ratio of atomic weight and valency of dissolution. So, we have two laws and we need to use these two laws so that we can come up with a expression for material removal rate. Material removal rate is a very technical characteristics, and we want to use these two basic laws to try to come up with the expression for material removal rate. So, what was the first statement? The first statement was amount of material dissolved or deposited is proportional to charge. So, this is the statement given in the mathematical form. Mass is proportional to charge. What was the second statement? Second statement said the amount of material is proportional to electrochemical equivalent, and which is the ratio of atomic weight by valency. So, now I can combine this expression as well as this expression, these two, so to say, expression, mathematical expressions, to get the third one, which says combining this, mass is proportional to charge as well as atomic weight divided by valency. So, it is a very nice expression, and once again charge is nothing but current, how much current I am passing for what duration. So, IT into atomic weight divided by valency. This can be expressed in an equation form, not proportionality form, like amount of material dissolved or machined or deposited is equal to I, amount of current pass, into time into atomic weight divided by valency, and now I have a constant which is the Faraday's constant, and Faraday's constant, the value is 96,500 coulomb. Okay. So, this is my constant. So, I can say if the total amount of charge passed is 96,500 coulomb, then amount of material removal would be exactly equal to the atomic weight divided by valency. So, if your atomic weight is 10, valency is 2, your mass dissolution would be 5 grams. Now, this is the amount of mass dissolved. Now, we want to get material removal rate. Material removal rate, if you remember, is typically expressed in volume, millimeter cube per second or millimeter cube per minute. So, amount of material dissolved divided by time, that gives kg per second, divided by density will give you material removal rate. So, the earlier expression was ITFV into A, that stays, which divides by T by rho. So, we get this particular expression. So, material removal rate ultimately is proportional to current, it is proportional to atomic weight, it is inversely proportional to the valency, it is inversely proportional to density, and there is a constant which is Faraday's constant. However, this particular modeling that we have done is for elemental material. That means, if you are machining only nickel using electrochemical machining or only iron using electrochemical machining. But as you know, in engineering application, generally elemental materials or metals are not used. Typically alloys are used, and what are alloys? Alloys are typically the solid solutions of different elements. Say for example, steel is an alloy, Inconel 718 is an alloy, titanium 6Al4V is an alloy. So, all these are alloys where there are different types of materials. So, let us try to develop the MRR model for a typical alloy or any alloy for that matter. So, modeling of material removal rate for engineering alloys where you expect more than one element. So, I have denoted atomic weight by AI, valency by Vi, and weight fraction by alpha I, meaning thereby there could be, I could vary from 1 to n or 1 to 3, there are 3 different elements. Now, for passing a current of I with a duration of t, there would be a total volume removal which is gamma A. Okay. Now, what is that expression for volume removal? Gamma A into rho into alpha I, where which one is the weight fraction, would be Mi. What I am trying to say is that if you pass a current of I over a time span of t, you would remove a total volume of gamma A, out of which Mi, or for that matter M1, is the total amount of dissolution of the first element. How much is that? M1 is equal to gamma A times rho times alpha A. Now comes the same thing, Mi equal to Qi into Ai divided by F into Vi. This was the expression that we have obtained earlier as well. So, as if to remove M1 amount of material of element 1, you require Qi or Q1 amount of charge. So, Qi can be once again expressed as this, and using the expression available here, you can get an expression like this. Now, what is Qi? Qi is as if the amount of charge required to machine the ith element. So, how much would be my Qt? It is very simple. If I know how much is my Q1, Q2, Q3, Q4, I can simply sum up to get the value of Qt. However, Qt is also I into T. If I pass 1000 ampere of current for 10 seconds, I know how much is the total charge, and that is sum of all the charges, and I have the expression for one charge. So, I can simply sum it over all the charges to get a material removal rate as gamma A by T, because this was the volume removal, I took this much of time. So, I can simply get the volume material removal rate like this. Now, if you compare this material removal rate, which is for alloy, which is for an alloy and for an element, they are very similar. How they are similar? Material removal rate for an element is proportional to current. Here also it is proportional to current for an alloy. It is proportional to rho, it is inversely proportional to, here also it is inversely proportional to rho. So, where is the difference? Difference is, in case of elemental, this is proportional to ratio of A by nu, but here because it is an alloy, there it goes in the denominator and summed up. Why it is summed up? Because you have different weight fraction and different valencies and different atomic weight. Otherwise, if you look at the structure, they are very, very similar. Now, we have got the expression of material removal rate, but in during machining process, the tool is somewhere here. Where is the tool? During machining process, this is my tool and this is my workpiece. During a particular instant, there is a distance separating them h, and I am passing a current I through the cell over a time span dt, and when I pass a current of I over dt, the total charge involved dq is I into dt, and because of that passing of charge, there is further dissolution of this amount. So, what happens? Over time, this distance is going to increase. So, this is called dynamics of electrochemical machining, and as if we are not feeding the tool, tool is fixed here, it is not moving. So, we want to study what happens to this gap if the tool is not given any feed, no feed condition. That is what we want to study. How would you study? This is the statement, I amount of current is passed over a time dt, and in the process we get a dissolution of dH, and over a area of S. What is that area? If you go back to the previous one, this is the area S, that is the area of the workpiece. We already have the expression of I. What is that I? I is nothing but the ohmic drop V by R. This is my resistance. So, resistance can be written as resistivity into H, that is the distance, into S. So, this is my expression of I in terms of voltage drop, in terms of area of the electrode, resistivity and the distance at time t equal to 0. So, this is the expression of material removal rate, IA by F into rho into V. This is the standard expression, but material removal rate is also dH by dt into S, dH dt by S, because this is the rate at which the material is being consumed or dissolved into the area. So, I can write dH by dt in this particular form. What is the difference in this form? Here you have a suffix of x. X denotes that this is the equivalent atomic weight of an alloy, and as well as this is the equivalent valency, nothing more than that. So, in that way I can further simplify dH by dt into this, and in this particular expression what you can see is that this part is a constant. So, this part is a constant which has been taken out here, and we can say this constant is C. So, your dH by dt or dH dt becomes C upon H. So, dH dt becomes a function of H, and it is an inverse function. So, this is your C, value of C, and further for an alloy value of C can be written like this. This was for a particular element and this is for an alloy composition. Now, let us try to integrate this particular equation to see what happens actually. So, this is your equation. I need to integrate to see how H changes with time. What was H? H was the separation distance. So, I can integrate between initial and some value H1, and I get an equation like this. If I plot this equation, what happens? This is something like this. This is what? This is your H0, the initial separation between the tool and the workpiece. As time progresses, time is your x axis, as time progresses, the H increases in a parabolic manner. Why it increases in a parabolic manner? Because that is dictated by this particular equation. So, what happens? As it increases, the distance between the tool and the workpiece increases, and there is less amount of material removal gradually. Had the material removal rate been constant, this would have been a straight line. That is not the case, which says this particular expression tells us, or this figure tells us, that if there is no feed given to the tool, gradually the work distance between the workpiece and the tool is going to increase, and the material removal rate is going to fall, which is not a good thing. So, we have to do something so that we can maintain the material removal rate. So, for that we need to give a feed to the tool, and that is what we are going to analyze now. That is dynamics of electrochemical machining with feed conditions. Tool is no longer fixed, it is being fed. So, generally it is fed with a feed rate of F, that could be millimeter per second. So, earlier your expression was dH upon dt C by H, the same expression we are using, but this was under no feed condition. So, now I am giving a feed. So, your dissolution would be dH by dt. Now, under steady state it is expected, but there would not be any change in the distance between the job and the workpiece. If there is no change in the distance between job and the workpiece under steady state condition, this can be equated to the 0, and if it is can be equated to 0, C upon H, that becomes equal to F, or F becomes C upon H. Now, we need to see what happens to that steady state gap H star. So, what is H star? H star is the steady state gap. Under steady state condition, it would be dictated by C and F. That is, C is basically related to how much voltage you apply, how much current is passing through the cell, what is the alloy you are machining, and F is a set parameter on your machine tool. Okay. So, on that H star will depend. Now, this brings us to a very difficult question. What is that question? For a given value of feed and for a chosen value of current and all other parameters, I get a H star of 1.5 millimeter. Now, my question is, how do I ensure that whenever I am starting electrochemical machining, all the time that gap, initially that gap is 1.5 millimeter. What happens if I cannot maintain an initial gap of 1.5 millimeter when my calculated steady state gap is 1.5 millimeter? This is a very tricky question. You have set all the parameters, undergone rigorous courses in electrochemical machining and come up with a steady state value of 1.5. How do you ensure the gap is 1.5, or what is there any point spending time in setting the initial gap to be 1.5? That is what we are going to check now. First of all, is it possible to set H0 equal to H star? It is possible, but it takes time. So, should we do it? That is what we want to analyze. So, once again this is my basic expression, dH by dt equal to C upon H minus F, where F is the given feed and C upon H the dissolution, that is under no feed condition. Now, we are going to change the variable domain of H as well as T by variable transformation. So, we are basically transferring the domain, we are making them non-dimensional, nothing more than that, so that we can get a non-dimensional expression of ddt prime H prime, and that non-dimensional expression is also related to ddt of H, or that the rate at which the anode is dissolving. And now, what we need is, finally we want to see how this H prime is going to change, and that we will be trying to get by integrating this particular equation between, we will be integrating it between t equal to 0 to t prime and H equal to H0 prime to H1 prime, and if we integrate it, we get an expression like this, and this is the way the curve would change. What is there in the curve? It is a very interesting curve. This is my time or non-dimensional time, and this is my non-dimensional final gap. What is this? This 1 is the non-dimensional steady state gap, which happens to be 1. Irrespective of whatever is your initial value, whether it is 0, 0.5 or 5, this is for 0 and this is for 5, irrespective of your initial gap, gradually over time the same steady state value would be achieved. This is a very good information for us. what was the problem. If you go back to the problem, you would understand. Our problem was getting or setting the machine tool to a particular value of initial gap, and we were trying to understand what happens if we cannot set it, and what is the result. After analysis, we find that the result is something like this, and which is very in our favor. Irrespective of whatever be the initial gap, final value is saturating at 1, that is the equivalent gap. Thus, we can say irrespective of the initial gap, H prime bar or would be 1 or H would be equal to H star. So, it is very evident. So, from that we can get a value of feed rate which has to be set on the parameters. I hope you have got the point. H prime has to be 1. So, H prime was nothing but H upon H star. If you remember, H star was C upon F. So, this is the transformation. So, from this expression we can get a value of F which we have to set on the machine, and that depends on what is the voltage you are going to apply, what is the resistivity, and what is the alloy composition. F depends on that, and as well as it depends on the value of H, and ultimately you can get a value of F where this H can be cancelled out. How it can be cancelled out? We know that I equal to Vs by RH, I equal to Vs by RH, and here I am getting an expression by V upon RH. So, I can measure the current, and I can set the current on the machine. I know how much is the surface area. This is basically the material. So, I know that. So, how much would be the feed that has to be set? Once again, how much would be the feed that has to be set on the machine depends on your current which you are setting. It depends on the area of the electrode which you can measure, and it depends on the density, valency, and the atomic weight of the material you are machining. So, this is also known. So, that you can set, you can get a particular value of F, and this is basically the rate at which material is removed at the workpiece surface, and typically expressed in millimeter per second. Now, let us come to the equipment. What are the modules that are used in electrochemical machining? Typically, we have a power supply, we have a electrolyte filtration and delivery system, we have a tool feed system and working tank. Now, what are these? This is my electrolyte tank, this one is my electrolytic tank, this one. There I have a motor and I have a pump. So, it goes through a pressure reducer as well as a flow meter and a pressure gauge, and it enters the tool. Here the tool is a hollow tool, and this one is the insulation on the tool. You may ask me why we are going to provide insulation on the outer surface, because we do not want an overcut. So, the electrolyte comes like this and moves over the working surface, and gradually at this particular places you would have electrolytic dissolution. What is this? This is my power supply. So, this is the positive terminal, this is your this is my power supply, this is the tool. So, this is your negative terminal and this is your workpiece, which is the positive terminal. You require a tool feed system because this gap has to be maintained. So, you require a servo system for feeding the tool. Once machining has been done, sludges would be collected here, like so iron chloride or iron hydroxide. So, these sludges are to be removed. So, they are taken out by a valve, and this is a centrifugal filtering unit or a separation unit. After separation, sludges are kept here and the electrolyte is fed back into the system. So, this is the basic modules of electrochemical machining, and to summarize once again, you require a power supply, filtration unit, tool feed system and working tank. These are the basics of the basic module. Now, let us come to the application of electrochemical machining. As we have already said, under the characteristics of electrochemical machining, it requires electrically conductive work material. As long as your work materials are electrically conductive, irrespective of their mechanical properties, like what is their Young's modulus, what is their hardness, it can be machined. What kind of machining operation can be done? Let us come to that. Die sinking can be done in electrochemical machining, very similar to your EDM die sinking. Profiling and contouring can be done. This is another very important application area. Tree panning can be done. Electrochemical grinding. This is a technology in its own right. Drilling can be done, and another very emerging area of electrochemical machining is micromachining. We are not going to address that, but out of these few applications, now we are going to go into their schematics. What is die sinking? Die sinking is shown here. This is your tool material and this is your workpiece. So, gradually the tool is fed in this direction, so that you can get a negative impression of the tool on the workpiece. Why is it called die sinking? Because in this manner, typically dies which are of very complicated geometry, they can be made. This is 3D profiling. Say here this is your workpiece and this is the upper part of the tool. So, tool 1 and this is your tool 2, and this is having a very complicated profile, as you can see in the 2D, but it can also have a 3D profile. So, the tool 1 comes down and tool 2 gradually goes up to give you a very complicated complex workpiece. Now, this is the drilling operation which we have shown earlier as well. This is your tool and this is a hollow tool. As you can see, there is a hollow hole inside, and the electrode is pumped through that hole and it moves like this, and on the tool there is also insulation, so that we have already said there is insulation on both the sides. Why there is insulation? Already we have mentioned that there is a problem of overcut. Once you give insulation, there would not be any electrochemical action here. We want the electrochemical action to be restricted just below the tool surface. However, you cannot restrict it here, so there is some machining or overcut. At least by insulation, the overcut can be reduced to some extent, and this way you can drill a hole, and the hole can be a large hole as well as small hole, or it can as well be of complex shape. Now, let us come to the tree panning operation. In tree panning, you want to make a large hole and you want to remove the centerpiece. The technology is very similar. Electrolyte is forced to this, and once again here also you can put insulation, and this way very large holes can be tree panned. Now, let us come to the quiz part of it. Quiz part of it in any of these lectures are very interesting. They are not exactly knowledge based things. You need not have to memorize things to answer these quiz. They has been designed in such a way you can reason it out. So, let us come to our first question. What is our first question? For electrochemical machining of steel, so my work material is steel, what has to be used as an electrolyte? What are the options? Option is kerosene, sodium chloride, deionized water and nitric acid. Which one should be used? We already know that kerosene is typically a dielectric medium, and it is used as a dielectric medium in electrodischarge machining. It is not going to ionize very easily. You require much higher voltage to ionize it. So, kerosene is definitely not used as an electrolyte. Deionized water, this is not tap water. Deionized water is once again a dielectric, and it is used in where EDM. So, as because this is dielectric, as because it is deionized, it does not have so much of ions, so it will not ionize easily. It requires higher ionization potential, so you do not use it. So, ultimately you are left with sodium chloride or nitric acid. Both of them can be used as an electrolyte, but nitric acid as such reacts with most of the material very violently. So, you cannot control the anolytic dissolution. So, your choice is ultimately sodium chloride, not nitric acid. So, in this way, for most of the questions you can reason out and get to the correct answer. Let us come to the second one. Material removal rate in electrochemical machining depends on. We know electrochemical machining process can be very easily modeled by Faraday's laws of electrochemical dissolution. We also know electrochemical machining process is a non-traditional machining process. So, the material property, mechanical properties of the material does not really matter. So, what are the options given? Hardness. Hardness of a material is very important in conventional machining, say turning, milling. but it is does not matter as far as electrochemical machining is concerned. The third option given is thermal conductivity. Thermal conductivity quite often is important in non-traditional machining process. We need not throw it away, but if the basic process is thermal in nature, then only thermal conductivity comes into picture. Otherwise, thermal conductivity do not have any role. Say for example, in laser machining, thermal conductivity will play a role. In electro discharge machining, thermal conductivity would play a role. But as we know, electrochemical machining is a electrochemical dissolution. Thermal conductivity has no role in that. Next one is ductility. Ductility plays role in conventional machining processes as well as mechanical non-traditional machining processes. So, in electrochemical machining there is no role. So, we are left with atomic weight. Why atomic weight? Why is it important? Why is it is the answer? Because we know electrochemical dissolution follows Faraday's laws of electrochemical dissolution, Faraday's law, and that says your mass of dissolution is proportional to charge, and it is also proportional to electrochemical equivalent, which is nothing but atomic weight upon valence. So, definitely this is the correct answer. MRR in electrochemical machining does depend on atomicity or atomic weight. Now, let us go to the third and the fourth question. ECM cannot be undertaken for, four options are given: steel, nickel based superalloys, aluminum oxide and titanium alloys. Out of those four options, steel is a metallic alloy and it conducts electricity, it is electrically conducted. Nickel based superalloys, though their thermal properties are very high, the thermal conductivity is very poor, they are electrically conductive. Same goes for titanium alloy, though their thermal conductivity is less, but they are good electrical conductors. So, these three things can definitely be machined, because one of the basic requirement of electrochemical machining is that your work material has to be electrically conductive. So, out of the given four options, the three options steel, nickel based superalloys as well as your titanium alloy satisfy that criteria. So, what we are left with? We are left with only one candidate, which is aluminum oxide. We know aluminum oxide is a ceramic. You must be knowing by this time, this is also used for machining steel. This is used as an ceramic inserts, and they are electrically insulating. Thus, this is the answer. As because it is electrically insulating, electrically does not conduct, it cannot be machined under electrochemical machining. So, your answer is aluminum oxide. Commercial ECM, the next question. Commercial ECM is carried out at combination of low voltage and high current, low current and low voltage. Out of all these options, low voltage and high current is the answer, because to do the ionization in a salt solution you require really low voltage. Why high current is required? The answer is once again M is proportional to Q. Either you pass high current for a short duration of time or very small current over a long duration of time. The first one is definitely economically much more beneficial. So, the answer is low voltage, which comes from the technology, and high current, which once again comes from the techno-economic viewpoint. Now, let us go into the solved problems. Today we are going to discuss three different solved problems which represents the domain of electrochemical machining. The first one is in electrochemical machining of pure iron. So, we are starting with a very simple assumption, it is pure iron. A material removal rate of 600 millimeter cube per minute is to be obtained or is required. Estimate the current requirement. So, the estimation is very simple. We know MRR is nothing but is proportional to atomic weight, current and valency and Faraday's constant. So, from that if we put those values, this is in cc per second. So, it comes here material removal rate, 56 is the atomic weight of iron, 96500 is the Faraday's constant, 7.8 is the gram per cc is the density, and 2 is the valency of dissolution of iron. So, using this expression you can very simply get a current of around 268.8 ampere. So, there are two things to learn from this particular example. What are they? One is how much amount of current is required. It is around 270 ampere. There is another thing to learn. It also indicates how much is the material removal rate, which is typically 600 millimeter cube per minute. We have two more problems and we will go into them gradually. Next one, this is a bit more difficult problem. Composition of nickel based superalloy is given. So, it is having nickel, chromium, iron as well as titanium. Their percentages are given, their densities are given, their atomic weights are given, even their valency of dissolution is given. All these things are given. So, what we need to calculate first is their density. What is the density of the alloy? And density of the alloy has been calculated using this particular expression. Once the density is known, density of the alloy is known, using the standard expression of material removal rate, we can get the material removal rate as 2140 millimeter cube per minute. And what is the rate of resolution? In the problem, the area was given as 1500 millimeter square. So, I can also get the rate of dissolution is around 1.53 millimeter per minute. Now, let us go to the third problem. In ECM operation, it says pure iron is of pure iron, an equivalent gap of 2 millimeter is to be kept. Determine the supply voltage. If the over voltage is 2.5, resistivity is given as well as set fade rate is given. So, how do we solve the problem? H star, we have to find out that expression. H star is the equivalent gap, which is C upon F. C we can calculate because all the parameters are given, but it has to be calculated as a function of F, function of voltage applied, which is V minus 2.5. In this way, you can find out how much is the voltage applied, which is 8.73. Here in this particular problem, there is only one area where you may face problem, which is this. This is the voltage. Over voltage was given as 2.5 volt. So, the actual voltage is V minus 2.5 volt, and from that expression you have to get the actual voltage. So, let us come to the summary of today's lecture. We have already gone through the electrochemical machining process, and now you can associate electrochemical machining as a non-traditional machining process. You have also understood the basic working principle of the electrochemical machining process. You can draw as well as find out what are the different tool potential drops. You know the material removal mechanisms of electrochemical machining, as well as you can model it, that is very, very important. You know what are the process parameters, models have been developed. Dynamics of ECM is very, very important, that has been analyzed, and another important area is different modules of ECM equipment has been talked about, along with typical applications. So, with that we come to an end of today's lecture. Thank you so much.